that's the team. They've worked a lot on algorithms like Ankur and learning theory, and so they'll be talking about edit distance robust watermarks. So please take it away.
Cool. Thanks, Ankur, and thanks for the invitation to come speak. So I'll be talking about edit distance robust watermarks, and this is joint work with Ankur. So in recent years, there's been a lot of proliferation of AI-generated content. It's appeared online. It's probably appeared in papers you've written. It's probably appeared in reviews papers you've read. It's appeared in reviews you've read, and it's appeared maybe in audio that you've listened to. And as such, there's been a lot of anxiety over this proliferation of AI-generated content online. There's studies that claim that over half of the content on the internet is AI-generated, and as such, there's various concerns, such as potentially this AI-generated content may be hurting search results, it may be making it harder to ensure that Wikipedia remains factual, and it may be actually making it harder to train new AI models, because there's some evidence that if you train an AI model on synthetic data from scratch, it won't be as good as an AI model that's trained on natural or human-generated data. And there's many risks from this. There's one kind of humorous example from a few months ago where Google incorporated AI into its search results, and then the AI started recommending that people eat rocks each day. So hopefully people are smart enough not to actually follow this advice, but there are that people eat rocks each day. So you should eat one small rock per day. I wouldn't recommend it. But. So this is a little bit funny, but there are some very much not funny risks of the fact that AI can potentially increase the amount of misinformation online, and this can have very serious consequences. So as a result of this, governments have taken notice, and last year the White House released an executive order on the safe, secure, and trustworthy development and use of artificial intelligence. And this executive order outlined a bunch of plausible solutions or mitigations to these challenges. And one of the mitigations they recommended was labeling synthetic content, such as using watermarking. And so watermarking, which is the topic of this talk, represents one tool amongst many which can help us to mitigate some of these challenges associated with the spread of AI-generated content online. Okay, so in this talk, I'm going to talk about watermarking language models. And I first have to tell you what a language model is. So associated to any language model is a vocabulary, which I'll call sigma. And this is a set of possible tokens. So what is a token? Roughly speaking, you should think of a token as corresponding to a word. This isn't quite true. There's some subtleties here, but for most of this talk, just when I say token, think of word. Now, what a language model does is it takes as input some sequence of tokens, say T1 through Ti-1, and it outputs a probability distribution over the next token, which I'll call Ti. And so I'll denote this distribution by model of Ti equals x for each possible value x of the next token, given the sequence of tokens T1 through Ti-1. And so, for example, you might have the sequence of tokens, DNA or deoxyribonucleic acid is the molecule that carries the blank. And the GPT-2 model will output the following distribution. It will say DNA is probability 0.4, most is probability 0.04, and so on and so forth. So associated to any language model is a canonical generation algorithm, which samples a sequence of tokens autoregressively. And so in particular, for each index I, given the sequence of tokens it's already generated T1 through Ti-1, we're going to sample Ti from this model's output distribution and then continue for some total length. And throughout this talk, I'm going to fix the length of the generated output of the model to be some integer L. And so in particular, for any model, I'll assume that it always generates outputs of length L. Of course, this is not realistic. I'm just making this assumption for simplicity. Okay, so this talk is going to be about watermarking language models. And let me first tell you, roughly speaking, what a watermarking scheme is. It's a way of embedding some subtle pattern in a language model's output so that, first of all, we have undetectability. And what this means is that the subtle patterns, the watermark that we embed, should not significantly change the output of the model. So in particular, if we ask ChatGPT to generate an essay for us, it should look the same to some external observer to an essay that's generated by a watermarked version of ChatGPT. The second requirement that we want of our watermarking schemes is robustness. And what this means is that we should be able to recognize watermarked output of some language model as originating from the language model, even after we make some perturbations. So if I ask ChatGPT to write an essay for me, and I don't exactly like it, I might remove some words, insert some new words. I still want the resulting essay to be detected as watermarked, as long as the number of edits I make isn't that large. Finally, I want soundness. And what this means is that if I generate an honest output, say I write an essay by myself without using ChatGPT, this should not be recognized as watermarked. Okay, so this is a rough overview of the three properties I want from watermarking schemes. Now let me go into some details about, formally speaking, what these properties actually are. So kind of a more rigorous definition of these three properties. So formally speaking, a watermarking scheme consists of three algorithms: a key generation algorithm, a watermarking algorithm, and a detection algorithm. The key generation algorithm outputs some secret key. So just think of this as a random string of zeros and ones. Now, given the secret key as well as a prompt, such as the question, what is DNA? The watermarking algorithm will output a sequence of tokens or text. It might respond with DNA or deoxyribonucleic acid is a molecule that carries blank. And finally, there's a detection algorithm. So what this does is this takes as input some sequence of text, such as the response to the output of the watermarking algorithm. It also takes as input the secret key, and then it outputs a single bit, 0 or 1, representing whether or not it detects this sequence of tokens as being watermarked according to the secret key. As I mentioned, we want these three algorithms, key generation, watermarking, and detection, to satisfy these three criteria. So what do these three criteria mean more formally? Let me start with undetectability. So roughly speaking, undetectability says that the result of two experiments should be roughly the same to any polynomial time algorithm. The first experiment is the following. We're going to generate a secret key from a key generation algorithm, fix a prompt, and then generate multiple samples from the watermarking algorithm for this fixed secret key. So we might get, for instance, multiple similar answers to the question, what is DNA? What we want is that for any polynomial time distinguishing algorithm, the output of the distinguishing algorithm, when it sees these samples from the watermarking algorithm, to be very close to the output when we make the same prompt and we ask the unwatermarked model to generate multiple samples. In other words, it should not be possible to distinguish basically multiple samples from the watermarking algorithm and multiple samples from the unwatermarked model. And in particular, as a corollary of this, basically the quality for any polynomial time computable quality metric will be the same for the watermarking algorithm and the true model. The second property that we want is robustness. And in particular, we're going to want robustness to edits, which means insertions, deletions, and substitutions. And as was alluded to in the previous talk, the key challenge here is dealing with the offsets that come up when you make insertions or deletions to your text. What we want is that, once again, over the random choice of secret key, and the output of a model of the watermarked model given some prompt, if we pass this output through some noisy channel that picks a constant fraction of indices and either inserts, deletes, or substitutes tokens at these indices, what we want is the detection algorithm for that same secret key that we use to watermark this text will output watermarked with very high probability. And in particular, I want the probability to be 1 minus some negligible function of a security parameter, which is related to the length of the secret key. Now, one trivial way to get undetectability and edit robustness is simply to let a watermarking scheme be the true model and just output watermarked for all possible text. This satisfies these two properties, but it's not very interesting. And the reason for this is it doesn't satisfy the third property that we want from watermarking, which is soundness. So what soundness requires is that for any fixed sequence of text, which in particular is generated independently of the secret key, the detection algorithm outputs watermarked. The detection algorithm outputs watermarked with very small probability, in particular probability that's negligible in the length of the secret key. so these are our 3 requirements. And now let me discuss some prior work in terms of how it meets or fails to meet these 3 requirements of undetectability, edit robustness, and soundness. So the first category of papers I'll discuss is by Christ Gunn and Zamir, and some follow, and several other papers, which get undetectability and soundness, but not the sort of edit robustness that we want. They do get some degree of edit robustness, maybe only to a sub-constant fraction of edits. And so what I mean is that as the security parameter goes to infinity, the fraction of edits that they get robustness to goes to 0. And the idea behind these schemes is very simple. You just take some watermarking scheme with no robustness, and you just repeat this thing multiple times. And as long as the edits preserve one of these copies, one of these blocks, so to speak, then we'll still be able to detect the watermark.
So now, these properties intuitively they make sense. You should define them going formally, but some of them could be made significantly stronger. Do you care about this variation? Soundness, you can say even if you see some samples output, you cannot output a string which is far. I'm saying, will you care about kind of qualification of the attack? Just you care about neural.
You mean for undetectability?
Well, for both soundness and detectability, robustness, you can have various flavors of definitions depending on the type of error, the capability of the attacker, what he sees, what can be called post-marking and detection. Will you care about the subtleties, or because you were describing which schema you want, right? Because it depends on the definition, right?
So I'm not sure exactly what you mean. You mean
for each of those notions, like in detectability, I can give you 5 definitions of various strands. So in your talk, will it matter those distinctions? Or?
I guess what I mean is undetectability for any polynomial time algorithm. Okay, I'm not sure what other variant you're thinking of. I guess I will discuss some other. Okay. Okay. So one of the other schemes that gets a stronger notion of robustness, but it's a little bit worse than the undetectability front is this paper that Rohit will talk about in a few minutes. So there they get robustness to a more like a constant fraction of edits. They get soundness, but they're not undetectable. They satisfy this weaker notion of distortion freeness, which means that the watermarked model is indistinguishable from the true model if you're only allowed to make one query. So you get one text sample.
But edit still means just replacing a token by another one and not deleting it?
They allow for deletions and insertions.
Oh, they allow deletions and insertions. Yeah. Okay.
It's undetectable by an outsider.
Yes, so it does not see the secret key.
It's allowed one query.
One query, yeah. I'll say more about this in a moment.
And also this closeness is also with respect to the randomness that goes into the generation of the secret key. So once the secret key is fixed, then the game is over.
So the last kind of prior work I'll talk about is by the paper that Miranda just talked about. And what they show is undetectability and soundness, but their work does not have particularly strong edit robustness. They're able to show robustness to a constant fraction of adversarial substitutions, but in general, they can't handle adversarial insertions and deletions. They do handle, say, IID deletions under some additional assumptions. And what our paper does is able to get undetectability, edit robustness to a constant fraction of adversarial edits, as well as soundness. And I mentioned there's also some other papers, such as the scheme that Scott talked about and many others, which kind of lose out on some of these fronts. Okay, so before telling you exactly what our main result states, I want to motivate a couple of these notions that we get. So why do we want edit robustness? I think this is pretty intuitive, so I'll go through it kind of quickly. Why not just substitutions? Well, most applications of editing sequences involve insertions or deletions. So for instance, when we edit essays, we're going to insert some text or delete some text. But also for other applications of sequence modeling, like for DNA, there's insertions and deletions and not just substitutions. One other interesting motivation for dealing with robustness at all, and in particular edits, is the process of tokenization itself. So this is the one slide where you can't think of token as being synonymous with word. This is because the way that a language model actually works is it outputs a sequence of tokens, which are, you can think of just IDs. So for instance, for GPT-2, there's a set of 50,000 tokens. And so an output of GPT-2 might look like a sequence of 6 tokens like the ones shown here. Now, in order to convert this sequence of tokens to text, you have to pass the sequence of tokens through some decoding algorithm, a tokenizer, which then outputs some sequence of text. So for instance, for GPT-2, this sequence of tokens corresponds to DNA as a molecule. But then because our watermarking algorithm acts on tokens and not text, in order to do detection, we have to encode this back into tokens. And when we apply the encoding operation, we will get a sequence of tokens that looks different from the initial one. In particular, we've taken the first 3 IDs and compressed them into a single ID. In particular, we have a net 2 deletions. And ultimately, this comes about because there's not a one-to-one mapping between text and tokens. That's one more motivation for edits. And of course, why do we want a constant fraction? Well, first of all, we want to get something that's as robust as possible, but also it's a gold standard in related areas, such as encoding theory. Okay. And the second kind of motivation slide is, why do we want undetectability? I want to contrast undetectability with this weaker notion of distortion freeness. So recall that undetectability says that no polynomial time distinguisher can tell between multiple samples of our watermarked model and multiple samples of the unwatermarked model. The weaker notion of distortion freeness says that any distinguisher can't tell between a single sample from a watermarked model and a single sample from the unwatermarked model. The problem with distortion-free watermarks is that they can suffer from insufficient diversity in the model outputs. And diversity is very important for certain applications. For certain reasoning tasks, it's common to do something like top K sampling, where you generate K samples from your model for some large K and then pick the best according to some quality metric. But if your model is not very diverse, then top K sampling won't work very well. And just to give you a little bit of a toy example, here's a watermark which is distortion-free, sound, and robust. But it only will ever output a single sample from the model for a fixed prompt. What you do is just let the key generation algorithm sample some secret key, which is just a sample of text from the model. And then watermarking algorithm just always outputs the secret key. Because secret key is generated according to the model, this is distortion-free, but it's kind of not very good for most tasks because we only ever get a single sample. And of course, it's not undetectable because we can just call it twice. Okay, so now I can kind of go towards stating our main result. I think it's been mentioned in previous talks, but one requirement that we need in order to get. Oh, is there a question?
Yeah, maybe you already said it. Sorry if you already explained this, but could you just very briefly explain what's the kind of main points of difference between this work and the previous lecture?
Yeah. So. Sorry.
I think there's a delay on the screen.
Yeah, so we're able to get undetectability, edit robustness, and soundness. And the prior work was not, none of the prior works got all 3 of these.
But they do have some maybe more limited version of edit robustness?
They have some limited versions, like either some constant fraction of edits or only constant fraction of substitutions. Okay, so what we want is, if, for instance, if we're able, if we correlate our model with the prompt, output the declaration of independence, there's really no way to watermark this because all models and all correct answers will be the same. So the way we measure entropy is as follows. I'm going to define the entropy rate, which is simply the average over all indices from 1 to the length of the entropy of each token ti, given the prefix of tokens t1 through ti minus 1, divided by the log of the number of tokens, which in particular is the maximum possible entropy. And this entropy in the numerator is according to the actual model distribution. So the assumption throughout is that this entropy rate is going to be some absolute constant. And what our theorem says, roughly speaking, is that if the entropy rate of the model is sufficiently high, if it's some constant, then we can actually get watermarking schemes that satisfy these 3 properties. So more formally, what we show is that under an appropriate cryptographic assumption, for a security parameter lambda, which is just a natural number, there's a watermarking scheme for language models over alphabets of size that grow polynomially in lambda, which satisfies, first of all, undetectability with respect to all polynomial time algorithms. Second, it's sound, which means that for any fixed output, the probability that we detect it as watermarked is only negligible in the security parameter. And third, it's robust to any constant, or to a small enough constant fraction of edits when the entropy rate of the model is at least alpha. And so the thing to note here is that alpha, this constant entropy rate, is showing up in the exponent of the size of the alphabet. So we require quite a large alphabet for this to work.
Empirically, what should I think of as like some range for alpha that's reasonable?
I'm about to discuss that. So, is this set of assumptions reasonable? Is this practical? Let's work through an example for GPT-2. So for GPT-2, the size of the alphabet, as I said, is about 50,000. And we want this to be at least lambda to the 1 over alpha. What is the entropy rate? Well, the binary entropy per token turns out to be about 4, which is about 0.28 times the log of 50,000. And so alpha ends up being about 0.28. Now, unfortunately, if you want lambda to the order 1 over alpha for some constant in the exponent times alpha to be less than 50,000, you ultimately need lambda to be very, very close to 1. And this basically means that we don't get any non-trivial guarantee. The good news, though, is that there is a sort of hack that we can do to make this thing kind of work in practice. And this hack consists of grouping tokens together. And so in particular, for some sequence where maybe initially tokens correspond to words, I'm going to create mega tokens, which correspond to groups of, say, like 3 words. And I'll give an example here. And if we were to, say, literally group sequences of 3 consecutive tokens together, we're changing the size of the alphabet from sigma to sigma cubed. But crucially, we don't change the entropy rate, because both the entropy per token increases by a factor of 3, and also log of the alphabet size increases by a factor of 3. And if we make sigma much bigger like this, we can actually make it more plausible that lambda to the 1 over alpha is actually less than the size of this new, much larger alphabet. And so we have some preliminary experiments where we do something like this. We have a slightly different way of grouping tokens together that is robust to a certain type of edits. And we have some very preliminary kind of just proof of concept experiments which show that you can get something that's robust to a very small fraction of edits. I want to emphasize this is not the best way of watermarking GPT-2 even for these parameters, but this is kind of just maybe more of like a proof of concept saying that there may be some additional hacks that you can do that will make this much better.
It changes your error rate by a factor of 3, number of tokens that you group together.
Exactly, yes. So we're losing out in robustness by a factor of 3.
It seems to be similar to
When you talk about insert and deletes of tokens, it's of individual tokens, right?
Yes. So actually, if you just group tokens together like this, there will be offset errors, and so this won't actually work. You have to kind of do something a little different, where you let these mega tokens be something a little different ways of grouping tokens together.
But that corresponds also to the changes that people.
Oh no, it doesn't. So sorry, you get we were able to get the same notion of insertions and deletions, like just individual tokens, not mega tokens.
How does it compare with Skotsky? Because now, like grouping token, it looks like this K tuples. I forgot how you call it.
It's still undetectable. So you can when you group tokens together, you have to it's also more computationally inefficient because you have to somehow compute each step you have to compute a distribution over more tokens. There are some additional hacks to making that work as well. So
saying even theoretically, it's an improvement. Even if you just say, okay, now you lose a factor of K in the number of errors. If you compare to Scott's scheme, you're saying it's better. And I'm trying to see because it starts to look very similar, right?
Also, crucially, he's grouping together a constant number of tokens instead of undetectability.
Well, it depends on the entropy rate. In practice, you can say Scott just needs K to be large enough so that things don't repeat.
But it's very different. We're not doing any sort of the pseudo-random function where you take K things and you compute a hash. That's not what we're doing. This is just to kind of increase the size of the alphabet. We're not actually changing the distribution of the alphabet.
I don't change the distribution over the tokens either. I do something different with it. But,
Okay, yes,
but you're getting, the cryptographic indistinguishability, right? That's the key thing that you're getting. I would say that on the.
Yes, yeah.
Oh, sorry, I think
Maybe I'll get to this eventually, but in terms of like practical uses of like your scheme, have you been able to implement this for like teaching, for instance?
Yep.
Like, how many tokens do you need in general to like detect it with 1%?
Several hundred.
Okay, but it's still something like feasible, right? It's not like millions.
It's feasible in the sense that you can implement this. There's several additional caveats that I haven't mentioned. So it's not hopelessly impractical, but it's not. I wouldn't say it's practical yet.
And are you going to go into detail about how you do the grouping of tokens? So like,
I can talk about that offline. This talk is more in the theory. So this is more of a kind of a hacky practical scheme that I just want to put out there as maybe like some advertisement, but this talk will really focus on proving the theorem. Okay, so now I'm going to move on to the proof of the theorem. And in particular, I want to discuss, there's going to be two steps to proof. The first step is constructing a type of code known as edit-robust pseudo-random codes. These are similar to the pseudo-random codes that Miranda talked about. And the second step of the proof is actually showing that edit-robust pseudo-random codes imply edit-robust watermarking schemes. I can first tell you what a pseudo-random code is. Given that I've defined watermarking, the simplest way to define a pseudo-random code is simply a watermarking scheme for the uniform language model. And that's it. So what do I mean by uniform language model? It's simply the language model that takes that ignores its prompt, so it has no prompt, and it just outputs a uniform distribution over sequences of tokens of some fixed length L. Now, in case you've forgotten or you don't exactly remember what a watermarking scheme is, let me just quickly review the three properties. So first of all, we want undetectability, which means that no polytime algorithm can distinguish between the multiple outputs sampled from our watermarking algorithm and multiple independent samples of uniform random text. Second, we want robustness. So we're going to actually have two different notions of robustness that I'll consider in the course of the proof. Edit robustness means that we have robustness to a constant fraction of edits, which means that if you take an output from a watermarking model, make a constant fraction of edits, it still is detected as watermarked. And we also sometimes will talk about substitution robustness, which is the same, but we have a constant fraction of substitutions as opposed to just edits more generally. And finally, we want soundness, which means that independent text is not recognized as watermarked with high probability. So in the rest of this talk, I'm going to discuss how we can construct edit-robust pseudo-random codes, namely these key generation watermarking and detection algorithms that satisfy these three properties. I won't discuss step 2 here, which is how you go from edit-robust PRCs to edit-robust watermarking. I'm happy to talk about that offline.
I just include if I remove one word and I put a bunch of words instead.
Yeah, so that would be like one deletion and like a bunch of insertions. Okay, so how do we construct these? Well, the first step in constructing edit-robust PRCs is actually to construct substitution-robust PRCs. So these are exactly the things that Miranda talked about. We have a slightly different construction, so I'll say a little bit about this. What we show is that under an appropriate cryptographic assumption, there is a binary alphabet pseudo-random code, which is robust to any constant fraction of substitutions bounded above by a half. Now, what is this cryptographic assumption? Roughly speaking, what it states is that log lambda juntas in the binary hypercube of dimension lambda form a weak pseudo-random function family. Now, what is a log lambda junta? It's simply a function, a 0-1 valued function, which only depends on log lambda of its input bits out of lambda total. Now, for those of you who aren't familiar with crypto,
The binary function?
binary valued function. Yeah. For those of you who aren't familiar with crypto, an equivalent way to say this is that log lambda juntas cannot be learned in polynomial time under the uniform distribution. So it's a hardness of learning assumption. Now, this prior work by Christ Gunn showed the same conclusion as their theorem, namely a binary alphabet PRC, but under a slightly stronger assumption. And to compare these assumptions, it's useful to consider Impagliazzo's 5 worlds. So Miranda Sam's construction relies on assumptions that imply public key cryptography. And so in particular, they live in cryptomania. In contrast, our assumption, only relies, is only known to imply primitives in minicrypt. In particular, it's not known to imply public key cryptography. So in this sense, we kind of have a weaker assumption, although I want to note that they're able to get a slightly stronger qualitative guarantee in a certain sense. Now, if I have time, I'll discuss the proof of this theorem. But for now, I want to focus on how we can take such a binary alphabet pseudorandom code and in a black box manner construct from it an edit-robust pseudorandom code. What we can show is that given such a binary alphabet PRC on length L strings, which is robust to any constant fraction of substitutions less than a half, say 1/2 minus epsilon, we can get a pseudorandom code with alphabet size some constant times the length, so O of L, which is robust to a fraction of edits which is very close to 1, so a 1 minus order epsilon fraction of edits. And one interesting property of this pseudorandom code is that it's actually not just robust to a large fraction of edits. It's also robust to an arbitrary permutation. So I can take a channel which makes a 1 minus order epsilon fraction of edits, and then take the output of that and apply an arbitrary permutation. We will still get robustness. In other words, we can still recover the watermark. And the same conclusion actually holds for our actual watermarking scheme, not just this pseudorandom code, which is the watermarking scheme for the uniform language model. But it does not hold for this little thing I mentioned about the empirical, this empirical implementation, which groups sequences of tokens together. Because obviously, if you permute these group sequence of tokens, the whole point of doing that just goes out the window.
Wait, but if the permutation respects the,
Respects them, then you're good.
yeah, like if it's larger than the chunks in which the tokens have been grouped, then you can permute and everything is still fine. You still pick up a signal.
Yes.
That seems significant.
Yeah, I think that is, yeah. So you can rearrange paragraphs and this sort of thing.
Yes, yeah, that's great actually.
But permutation is applied only once, so it doesn't matter, I guess.
Well, it doesn't matter, like permutation or permutations. Okay, so now I'm going to discuss how we actually prove this theorem that goes from binary alphabet PRC to a large alphabet, binary alphabet PRC with substitution robustness to a large alphabet pseudorandom code with edit robustness. Okay, so let's consider a substitution robust pseudorandom code, and I'll let the corresponding algorithms be keygen S, watermark S, and detect S. How does the edit robust pseudorandom code work? Well, roughly speaking, the idea is to use the indices of ones from the output of our substitution robust watermarking algorithm. And for this reason, we call it an indexing random code. And this indexing is the reason why we have a large alphabet, like order of the length, because the length of the binary alphabet pseudorandom code is L. Let me tell you a little more detail about how this works. So the key generation algorithm for edit robust pseudorandom code simply outputs the output of the substitution robust key generation algorithm. That's going to be some secret key. Now, how does the watermarking algorithm work? We want to produce some sequence of integers from 1 to order L, which looks random. What we're going to do is we're going to first call our watermarking algorithm for the substitution PRC. And this produces some sequence of zeros and ones of length L that looks random. Then I'm going to define this thing I call the index set, script I, which is simply the set of indices I from 1 to L, at which xi is equal to 1. And then I'm just going to output a uniformly random permutation of the elements of this index set. And the hope is that this looks random. So this will give a sequence of tokens, which I'll call T, which consists of integers from 1 to L of length order of L. And in general, the expectation of the length of this thing will be L over 2. Finally, how does the detection algorithm work? Well, it takes as input the secret key, as well as some sequence of tokens, such as that generated by this watermarking procedure or an edit, the result of passing this through some edit-bounded channel. And it acts as follows. Well, it first tries to reconstruct this sequence of bits x by letting for each index I from 1 to L, I'll let xi prime be the indicator that at least one of these tokens that lies in this list T is equal to I. Then I'm going to output the result of the detection algorithm for the substitution PRC on this string x1 prime through xl prime. And so, of course, if there were no perturbations whatsoever in this sequence of tokens, then xi prime would be equal to xi for each index I. And so I'll basically be good because the detection algorithm for my substitution pseudorandom code will output the text, the watermark text itself as being watermarked. So why does this work? Or why does something like this work? I first wanted to say about, explain why this gets edit robustness. The main idea is that insertions or deletions from the sequence of tokens T correspond to substitutions in the string X. Let me work through an example. If the output of our substitution PRC is some string X, 011001, the output of our watermarking algorithm might be this string 236 because the second, third, and sixth indices of X are equal to 1. If you pass this through some noisy channel which say inserts of 4, then the resulting string X prime that we use in our that we can recover in our detection algorithm will be the same as X, but the fourth index will be changed from 0 to 1. And similarly, removing a token from T will correspond to changing some index of X from 1 to 0. So this does work. If you kind of just use this basic correspondence, you can get robustness to some constant fraction of edits. It turns out that the particular constant fraction of edits we're able to get robustness to is actually a little bit too small for our application of watermarking. We need robustness to a constant fraction of edits, which is very close to 1. And so to account for this, we actually have to add some additional components outside of what I showed here. And as a consequence of this, the alphabet size will go from L to something that's a constant times L. But I'm not going to go into more detail about those additional components of our algorithm. Soundness is pretty immediate. It follows directly from the soundness of the detection algorithm for our substitution PRC. I think that's a little bit trickier is undetectability. So ideally, we want something like the following. We want to say that if the output of our substitution PRC is actually uniform, say X is uniform in 0, 1 to the L, then we want a uniform permutation on elements of this indexing set to also be uniform. So uniform on strings of length order L consisting of integers from 1 to L. Now, there's an obvious problem here, which is that this claim is false. First of all, the length of this string will be variable. It won't be exactly L over 2 in general. It will have some randomness. But more generally, maybe the bigger problem is just that there's a very easy way of telling apart such strings from random, which is that the output of this watermarking algorithm will always have the property that all of the individual elements of the string are distinct. Whereas a uniformly random string of length L, consisting of integers from 1 to L, will with very high probability have repeats. The good news is that there's a way to get around this. We have to add some additional components. So we have to add some perturbations to the output of this watermarking algorithm that basically creates some repeats. And it turns out that if you do this correctly, you can actually get undetectability. So in the last 5 minutes, I'm actually going to take a step back and discuss how we actually are able to construct this substitution robust pseudorandom code, which we then use as a building block in that edit robust pseudorandom code that I just talked about. So just to remind you, what I'm going to prove now is that under this cryptographic assumption, there's a binary alphabet pseudorandom code which is robust to any constant fraction of substitutions of less than half.
Remind me which cryptographic assumption you make?
Great. So it's going to be the existence of juntas that are weak pseudorandom functions. So basically, suppose we have some family of functions indexed by a secret key, which maps the binary hypercube of dimension lambda to 0, 1. What we want is that this is a pseudorandom function, so a weak pseudorandom function. So we make multiple queries of strings in 0, 1 to the lambda, and we want the output of these xi's that we make queries to, comma f of xi, to look indistinguishable from that of a random function.
I mean, one could always use a junta testing, algorithm.
Yes, but those require adaptive queries.
Ah, good.
And we're not allowed to make them. So we want it's a weak pseudorandom function, which means
Weak means non-adaptive.
non-adaptive.
Okay, thank you.
And how many samples are you allowed? Any polynomial? or-
Polynomial, yeah. So there's clearly a quasi-polynomial attack here. So you could conjecture that that's optimal. So we get anything sub-quasi-polynomial it might be.
And do you have a concrete candidate for this junta weak pseudorandom function?
Yeah. So actually, I drop the citation of the slide, but there's a paper by Bloom et al. BKFL 94, I think.
Okay.
So they have basically consider the function.
What's it based on? Yeah.
Yeah, so consider the function which let this, so the log lambda set is going to be random. I'm going to split them into two parts. Take the XOR of the first part, take the majority of the second part, and XOR them together. The conjecture is that this set of things is going to be pseudo-random.
You meaning within the junta?
Within the junta, so I split that log lambda into two
XOR half
parts.
of it, I majority half.
And the XOR
I
them
think
together.
Avram also has some money on whether you can beat it or not. So if it's like a k-bit thing, then there's a pretty simple like n to the k over 2 algorithm. And even if you can shave the n to the k over 2, you get 1,000 of Avram's dollars. So that's a lot of, I don't know if it's inflation adjusted.
That's not bad.
If it was 100 million, then it would be insurance for OpenAI to use this.
I don't realize
I
that
don't
enough.
know if Avram can spot that.
Okay, so given this assumption, how do we construct the substitution robust pseudo-random code? The key generation algorithm will just output the secret key for this pseudo-random function family. The watermarking procedure will act as follows. It will draw a polynomial number of samples from this uniform distribution on 0, 1 to the lambda. And then it will output more or less basically the concatenation of xi comma fsk, the pseudo-random function evaluated on xi, for each index I from 1 to polynomial lambda. And this produces some sequence of bits, which are just tokens in this setting. So I'll call this t, and it's of length polynomial in lambda. How does detection work? Well, we're just going to kind of take this sequence of inputs t. We'll unpack it as these pairs xi prime, yi prime, which correspond to the xi fsk of xi, the watermarking algorithm. And then we're going to output watermarked if and only if a strict majority of the indices I satisfy the property that yi prime is equal to the evaluation of the PRF on xi prime.
Wait, so you're interpreting each token as a concatenation of a random string and the output of your pseudo-random function?
No, the tokens are tokens are like the alphabet is 0, 1. So
Okay, then what is this xi comma fsk? So that's some
I'm just kind of, I should have just written like the concatenation of like x.
parentheses.
X. Sorry, there should be a parenthesis. Okay, so basically
How
just
do we get from that to the sequence of tokens?
just like output the bits of xi, then output fsk of xi, then output the next one, just concatenate them all together.
Oh, okay, and that gives me a sequence of bits,
Yeah.
which I then reformat as being tokens over my. I do want to get over this larger alphabet.
Oh no, we
I'm
only want to
still
binary.
over binary.
We're over binary. Yeah, everything's binary.
Got
Yeah.
it, got it.
And the junta can change from block. When you say junta, it means every output depends, like for every particular input, you read only a few positions, but those positions can change from input to input.
No, it's the same. It's this fixed thing.
So there is like always a fixed subset of things.
Yeah, there's a fixed log lambda subset. The secret key tells you what that is. Okay, so I think I'm almost out of time. Let me just say really quickly why this works. Basically, the only interesting property is substitution robustness. I'll assume for simplicity that we have an IID substitutions with probability p. The main point is that for each index I, these log lambda relevant bits of xi for determining the output of the junta all remain unperturbed with probability 1 minus p to the log lambda, which is just 1 over a polynomial lambda. And this gives me inverse polynomial advantage, so then I can repeat this polynomial lambda times and be able to get some statistical signal in terms of being able to detect text as being watermarked. So soundness and undetectability are fairly immediate, and I just want to jump to the conclusion. So what we have is the first undetectable edit-robust watermarking scheme. Of course, I did not talk about how we go from edit-robust pseudo-random codes to edit-robust watermarks, but that's in our paper. And there's lots of open questions. I think maybe the biggest open question is if we can get an edit-robust pseudo-random code with constant alphabet size. Thank you for listening.
Let's take maybe one quick question from the audience while Rohit sets up.
If you did have an edit-robust pseudo-random code with constant alphabet size, would that then also imply the edit-robust watermarking scheme?
Yes.
with constant alphabet size?
might be an important component of practicality.
Yes, I see that, I'm on watermark. This is not, this is but
There's a lot of separation of done terrorists, so it's too difficult for
I see that notes.
plenty of shooting.
All right. Cheers. It's using oh, okay. Okay. Sure.
At least some. 1 second before you start.
I see. All right.
Yeah.
He said, yeah, wait before starting.